something with your hair? You know what? The easy round up, round down.
Oh, you're doing that one problem with like the company. I just brought it up.
I don't know. I'm not sure. Like you could be right. Right in that area. No, I was trying to find
Then you round it up.
So like 4 point, if it's just one whole step size, it's more like 4.2. Is that round up to 5? But you know, our question on the other
Instead of opening like tires, like
And it's actually really easy. And it gives you an array, like array, and then you can just like pick the highest one.
Does everyone have the lecture worksheet? Okay, perfect. So if you don't have it, it's at the back of the class, or you can come down to me if it's already run out there. All right, let's get the class started. Hi everyone, welcome back from the spring break. How is the break? Does everyone get some sleep or relaxing time, hopefully? Okay, so today we're going to talk about the remaining part of the analog signal, the DAC or DACs, basically the digital to analog converters. Last lecture we talked about the analog to digital converter, and before that we talked a little bit about the analog signal overall. So this lecture will be served as the basically the ending of the last big chunk of the class. The next the next lecture is going to be a review section, and the next Tuesday is going to be a lecture on some less tested topics. So before we go to the DACs, some announcement. So homework 7 is due today at the midnight. We do notice that the DACs have some questions inside of the homework, so we do give you essentially removing the penalty of that 10% off. Wait, is there anything wrong with the site? Okay. Anyway, so we will not take 10% off if you submit tomorrow, but today is still be the official deadline. So tomorrow night we'll be releasing the answers to the homework, and then essentially we will not be accepting submissions after tomorrow at midnight. So that you guys can hopefully have more time to study on the content. Homework and the practice exams are the go-to resources as usual. And to the next big chunk, the exam 2. It's going to be this Friday. Same time as last time and the same place as last place. Each of you are divided, I think, by your last name on which room it's going to be in. It's going to be the same room as last time, and from 4:30 to 6:30. If you have some accommodation request, your test is going to be at 10:23 at your starting time, individual starting time. We might be running low on the space there, but if that was the case, we will give you additional instructions on where you take the exam. But that's pretty much the logistics for the exam 2. The content of the exam 2 will be covering basically from the interrupts all the way to the ADC and DACs, basically until today's lecture. We will do some testing, small testings over the first half of the class. It's not going to be heavily tested. There will not be any long questions based on that, mainly multiple choices, and maybe some small questions within the essentially the design questions, because they kind of work all together. On that note, maybe take a look at that pull up and pull down registers. I think a lot of you guys got it wrong in the first exam, and hopefully you do not get it wrong this time. The project proposal, we had a meeting, we have met with all the teams, and then we worked out basically what are the expected revisions you need to do on your project proposals. So the revision of this will be due this week after the exam. On Saturday, basically you will upload the document to the same Google Drive folder, but just with a name with underscore, revised or etc. to indicate this is a newer or updated version of that project proposal. And we will also be having the student presentation starting at 20th of the March, basically the next Thursday. we are currently assigning topics based on what you guys did in the proposal, in the final projects, and then we will basically send that to you guys once we finish assigning that. Each of the groups are basically going to be the same as your project team, and then you will come upstairs, come downstairs to this location and then give a 12-minute or so mini lecture to the whole class with about 3 minutes Q&As. Yeah, and before that, like after you finish the slides or etc., you should schedule like a 30-minute slot with the teaching team so that we can go over the content with you together, make sure they're all they're like sufficient enough, and also work on a little bit of your maybe what examples you want to get, maybe how would you present such content. So yeah, any questions regarding any of the announcement? Homework, exams, final project proposal, revision, etc. Anything? Okay, perfect. So without further ado, we're gonna dive into today's, this is like the outline of the entire analog signal section. So we have already finished the first two. So today we're gonna mainly talk about the DAC or DACs, the digital to analog converters. And more specifically, we're gonna first start with different types of DACs, just like when we did it with the ADCs. And then we will briefly talk about what type of DACs we have on the board we have in the class, as well as the, last but not least, the arrow types on ADC and DACs. We talked a little bit about like the quantization arrows in the last lecture. Not sure if you guys still remember it. It's a while ago. But that's one type of the arrows that essentially inherit to these architecture configurations. And then today we're going to look at a few other inherited arrows as well. So as usual, there are some additional readings if you want to do. We have the reference menu as well as the one of the recommended textbooks that have the entire chapter on the digital to analog converters. In there, they will cover like more like different types of the DACs and a little bit more on like the nitty-bitty of how exactly they're implemented on like more electronic and circuit side. We don't expect you to learn all those, but just have like a general ideas of how they work and kind of know how to calculate any of the output if needed. So let's go to the types of DACs. They are, so we basically, as usual, these things exist everywhere. We interact with it daily, especially as EECS students, especially if you work a little bit more on the EE or ECE side. There are a lot of applications or things we do with these DACs. For example, when we have like digital audios and we want to make them to like actual sound or like waves, basically. That's one of the components we'll be using. More on like the electronic testing side, we also have the, for example, in the middle, it's called like a signal generator. Not sure how many of you guys, you probably see it in the labs by now, and hopefully you used it by now. Basically, you input a bunch of parameters, what's the frequency, what's the peak-to-peak voltage, all these things, and then it will, based on that, those characteristics, generate a like an analog output from this output port. So from like a very high level, the general concept here is we, as just like the ADCs, we do those by steps, or in more our terms by like n bit of the resolutions. And then these are some you're probably gonna figure it out, basically these two formulas on how to calculate the output. Basically, we have like a reference voltage, just the same as when we did at the ADCs, and then we divided those by the amount of the bits that the current DAC is capable of, and then that gives you, whatever the steps each of these bits corresponding to, and then in the end, it will basically give you an output, DAC output, as an analog voltage. Yeah, for example, well, I hope this is pretty straightforward. Oh, yeah, any question?
Do they always output waves, or do they output
It could vary. It depends on how you configure it. The sine waves or these type of waves are the most common ones. You also can do like square wave, for example, or just like a constant on and off, a constant high or constant low. Although that might be a little bit overkill, but you could certainly configure it like that. All good? So yeah, this is like the very general concept. And then before we go into the actual configurations, let's give you a little overview on, what's okay, yeah.
I was just wondering why we subtract 1 from the digital value. It seems like if the digital value is 0, for example, that can cause problems just in general. It's like we could sort of never reach our VREF if we always subtract 1.
Yeah, the digital value usually, I think in this case, are from like 1 to 4, like, 4096, and then we minus 1 to just get it to the whole range of the bit. Right. That's essentially, yeah.
Does that mean we could never sort of achieve our VREF if it only goes to 4096? Then it would be, just a fraction of the VREF, not, 1.
That's a very good question. So you could configure it as either everything just run down or run up or in the middle. I'm not sure if you remember in the last lecture, we have basically you could decide whether the 0 starts at 0 volt or it starts at, say, the last significant bit, one step up, basically. So the essential reason of -1 is because we have, say, n values, right? There's only n minus 1 steps in between. So you can decide whether you want to like shift it up a little bit or shift it down. So it's essentially your own configuration. Usually people do, I think, just push everything down. Yeah.
Just sort of a follow-up to that, it sort of seems logical to me that we might want to change that 4096 to like 4095 because I remember like last time we had sort of an example where we had 2 to the n, when it really should have been like 2 to the n minus 1.
Mm-hmm.
If we want, 4095 steps, then if we change this 4096 to 4095, and the digital value, because it can only be 1 or 0, so it could never actually be 4095, then that would sort of achieve our goal of sort of ranging from 0 to VREF,
Mm-hmm.
with uniform steps, while being inclusive of both 0 and VREF.
Yeah, that's a very we could certainly do that. I think what people people don't usually get hung up on that 1 for a few reasons. First, usually you have like a 10-bit or 12-bit, for example. Then that 1 actually corresponding to like a very, very small amount. And the second, I think more importantly, is essentially we don't really know what the least significant bit, basically the quantization arrows. It could be within that 1-step range. So it could be either, say, one step of the DAC or ADC is 20 millivolt. It could be anywhere between 0 to 20. So it doesn't, in practice, it doesn't add any value, or it doesn't, how do I put this? It doesn't have like practical values to consider that 1 steps, because in the hardware configuration, that's basically your error range. It could be within that anyway. So imagine if you have like a resistor with minus or plus 1% of the error tolerance, then it could be anywhere there. And then if you hang up on that 1 bit, it doesn't make much practical senses. But I think essentially we could do that, but this is just how people do it nowadays, because we indeed have 2 to the n times of values with however amount of bits you have. You have n bits, and then you actually have those values, and you have 2 to the power of n minus 1 steps in between. So that's just how people do this nowadays. Hope that answers the question. Okay. So back to the main track. Basically, before we go into the actual hardware configurations of the DACs, it'll just give you some like hardware constraints on the actual circuit design. First is called like the loading effects. basically it occurs when the output of the DAC is connected to a load, which is usually a lot of times is the case. And then when these load are connected, though they will draw like additional current, and then that will affect the DAC's performance. These loads can be resistors or capacitors or any other like active circuits. So what we would do is we almost always have some amount of like internal resistance, like the R source here, and then the V out, and with the load on the output side, we're gonna have the actual output or the desired output is gonna be divided between the amount of the internal resistance, the R source, as well as the R load. That's the voltage divider equation. You guys are familiar with the voltage divider, right? Does anyone not sure what that equation does? Because this equation is kind of important for the next few slides on how we actually design the DACs from like a actual circuit perspective. Okay, sounds good. Hopefully you did, because that's also what we used back in the ADCs when we discussed the flash ADCs. Okay. So so what do we do about this? In practice, usually we add like an additional op-amp so that we can have essentially the V in on the positive end of the op-amp be held at roughly the same as the V out. And because of the R source usually is quite small, hopefully quite small, and then we could have something like approximately the V out approximately equal to UE desire. And the good thing about this is the output of basically the V out is not dependent on the R load to a certain extent. I'll show you this in like a circuit simulator. But you also notice that there's additional like capacitor here. This is a little bit optional. It's usually served as like a protection circuit. You could have it for like better circuit design, or you can also remove it. Depends on how you configure it. But usually we recommend to have this if you're doing with like some AC signals, for example. And let me show you like a circuitry for this two type of load. Basically, one on the okay, here we go. So on the top is basically like a banana version of what we just discussed, purely divided through like a voltage divider circuit. And then if we say change the load value, okay, even at this, if we have like internal resistance of 100 and the load value of like 1K, the output value is like roughly 4.5, while the desired value we want to output is 5 volt. So if we change the load value, for example, you will see that when we increase the load on the top here, basically the value starts to change. If we go up, then it goes up to closer to what we desired, because just by voltage dividing, the outside have more weight over this circuit. But if we go like smaller, for example, then we can see the V output is like dramatically decreasing from what we wanted as the desire, which is 5 volts. Meanwhile, on the bottom, when we add that one op-amp, the output here is kind of independent to like a certain extent, independent to what's the load value here. That would almost always held at 5 volts in this small circuit. So that is why, so this is like a very, I think, fundamental building blocks at the voltage. So basically, you will see we're trying to modify later a lot on the left side, but on the right side, it's almost always have some sort of op-amp connected in some way to help keep the load effect out of the equation. Yes.
For the nuclear boards, do they have the voltage buffer for their DACs like built in?
For which one?
The nuclear boards that we work with.
Oh yeah, they do have those, so you don't have to worry about that. Yeah, the ones you guys have are pretty good ones. So with that sorted out, let's go into the first type of DAC configuration, or like hardware configurations. It's called PWM filter. I hope you guys still remember our old friend PWM. Basically, this configuration is like probably one of the easiest or like the most simple way to build like a digital to analog converter, which is we basically have the PWM signal goes through like a low pass filtering, and the whole filtering basically smooths out your on your signal on like the rapid on and off switches. You can basically think of them when you have like a duty cycle of PWM signals that's larger than 50%, your output level is going to be gradually increasing. The equation to think about is basically the equivalent of the V out is pretty much equals to the duty cycle times the V reference. So if we gradually increase the duty cycle, then we could see like a gradually increase on the voltage, essentially the V out. And then when we gradually decrease the duty cycle, then we could have effect where the whole voltage out goes gradually down. Of course, you have to control these quite carefully, but this is like the concept behind this PWM filter, low pass filter configuration of the DAC. And of course, the previous one is like a more ideal situation. In real life, you're gonna almost always have some form of like distortions within each of these steps or each of these transactions. But gradually, if you just look from a distance, or if you shift it fast enough, then you could essentially achieve like a more or less smooth analog signals. Does the concept make sense? I will show you in like a circuit, the fail step basically on how actually it works. But this is the general ideas behind it. And then if we were to show you in the circuitry, and here we go. Okay, so imagine if, say, we start from here, and then I gradually increase. Is it going anywhere? You'll see a little, basically the tendency of going up, and then once we reach that, it's gradually going down, and if we do this like very fast, that's essentially the idea of behind this PWM triggered or PWM plus low pass filtering. Let's see if I can make the simulation much faster, and also curve speed faster, so that hopefully we can see something more smooth. Were you able to see that? So basically, it's some form of like sine wave analog signals outputted from the system. Although you will see on each of the stage there is a little distortion caused by the RC circuit, but if you do it cleverly and gradually, then you have like a pretty decent analog output. Does this part make sense to you guys? Basically, by changing the duty cycle of your PWM signal that connected to an RC circuit, then we are able to create this step-by-step increase or decrease of the voltage signal. And then when we combine these steps together, we essentially have a sine wave. They are all step-by-step, but Does this make sense? Okay. And then next is going to be called the resistance voltage divider, hence the name. This will be, if you look at this, it will look very familiar to what we talked about last time, the flash ADCs. Essentially, it have a bunch of resistors, the same value are connecting to each other. And then we selectively turn on and turn on one of the switches here, and then that will give you a value of the corresponding steps at each of here. Imagine if we have, say, if we have like 7 volts from here, the V reference, and then 0 here. So essentially, each of these step is 1 volt. And then, depends on what's the digital input here, 3-bit control. So this is like a 3-bit DAC configuration. Depends on which of these bits are put down, then one of the switches are put down, and then output a V out to the op amp, which holds that value on the output side. So in real life, usually they use like the CMOS switch, which is like much faster than physical switches like this, but the idea is pretty much the same. Yeah, basically like an inverted version of the flash ADC. You come in, that goes to basically each of these steps corresponding to the same amount of voltage level you could achieve. And then by selecting which switches is being put down, in this configuration, only one switch will be closed at any given time. Depends on where it's closed, the V out will give you an output voltage based on which steps you're at. Any question? Yeah.
Can you explain what the op amp is doing again?
The op amp basically, you can think of it like a holding stage, so that it kind of make the V out of the system independent of what's the load put on the outside circuit. Any other questions regarding this? I will also show you like a circuit design on how exactly it works. Okay, so let's do that. Basically, this is the again the 3-bit DAC design with the resistance divider. We have the same amount of values here, 100 ohms on each of these steps, and then the V reference is 7 volt. And then if we go to basically 000, it's essentially 0. You will see some small values, which is depends on how you decide to deal with your quantization arrows, push down, push up, but that's something that essentially going to be there. But anyway, once you turn 1 bit on, essentially that gives you a 1 volt, and then if you do the next bit, that gives you 2 volt, and then 3 volt, and then 4 volt, and so on, all the way until you can reach basically whatever the amount you have on the V reference. So this is a pretty straightforward design, and the challenge here is obviously just the same as the flash ADCs. First, you will need a lot of these resistors. Imagine this is only like a 3-bit system, right? If we have like 10-bit or 12-bit as normal, then you need essentially 2 to the power of n amount of the resistors. And the other thing is these resistors, because they come in sequence, and then each of them are connected to one switch. So these resistors has to be very high accurate in case you want to build this, chose something like 0.1% error tolerance, etc. But these, the accuracy of these resistors are actually quite important to build a precise DAC design like this. But this is very fast, so that's. Any questions on the resistance voltage divider configuration here? Yeah.
Can you put this through a low-pass filter to make it better?
Can we put this into low-pass filter 2 and make it better? I think in the end, the output, if you do want to have like a smoother signal, we could. I think a lot of times people actually do that for either ADC or DAC. They will add little RC circuit in the end. Depends on what's the range, but they will add like a small RC circuit in the end to make the signal smoother. But that was mainly for taking out of the little steps inside of not for what's happening underneath. But sometimes they do if it's like a lower bit configuration. Any other questions regarding this? Perfect. So now that you see like a bunch of switches here, right? What if like you want to close 2 switches or more at the same time? And hopefully also save some of the resistors that's dedicated to the, the 2 to the n power of n design. They are actually like a building block for that. This is what they call like summing amplifier circuit. So in this one, it's slightly different configuration than before, but it's still like op-amp. You don't have to know too much detail about how exactly they work, but basically the VOut here is served as the divider between this RF and whatever the combined value of this different Rins. And you can choose on how many of these different values are put into this the negative side of the op-amp. So essentially, what you added up is all of these voltages put it on this side all together, adding up together, and then divided by the RF, which is what we put here, as well as the Rin, which is the combined value of everything on the left, and then give you like a Vout. It's going to be a negative output, but you don't have to worry too much about that. There will be like a inverting circuit after that Vout. So, but this is like the general idea here. This is mainly served to like reduce number of resistors, so we could achieve something similar to the previous configuration, but with a lot less resistors. So a lot less complex hardware design, or like at least the cost-wise. And this is like a building block. So what we actually end up having is something. Oh, sorry. So this is one of them, and then we could build a little bit more on top of that by using only 2 number of the resistors values, basically R and 2R, and then have it like a configuration like this. This is called the R2R ladder configuration. So we can briefly go through like the math here. Basically, everything here is number like basically R, and then except for this one, which is 2R. And then everything on the parallels are 2R. So if you just combine them together, these two will become like an R together, and then plus this is 2R, and then another 2R together become R, and then added that. So basically, each of these node divided by divides the previous nodes by half. If that makes sense. Again, voltage dividers that we did before, but essentially these two in parallel, and then they add together become these two Rs in parallel added together become 1R, and that 1R in sequence with this R that became the 2R. So another 2R in parallel situation, and then just go all the way up. So each of these nodes here, from the top down, each of the nodes here essentially divides the value by 2. So conveniently, each of these switches here will corresponding to, depends on which index of the switches, is 2 to the n over 1, well, 1 over 2 to the n amount of the whatever the B references has. And then these switches can be individually put down or up, and then they combine together to be contributes to the Vout. So this is like a more, how do I say this? Like more standardized version of this. So instead of using like arbitrary number of Rs here, we just set it to be R and 2R, which makes like the manufacturing a lot easier, and then also make the cost significantly less, because we use the same amount of the resistance, but we only use the same values. Well, 2 values of them. Okay. Any questions on this or the equations here on how this is achieved? Okay. So just remember the voltage divider equation. They're going to be quite handy. And then again, let me show you one of the circuit simulator. So this is what we have. So this is the value R, this is 2R, so 50K and 100K. And then you can decide on whether you want to turn it off or on individually. So if everything is low, it's essentially practically 0. And then, if you started by the, okay, start here. You will have 1 step here, and then we have 4 bits, so in total, like 16 steps. So if you 1 up, this will give you 2 volt, and then 3 volt, and then, 4 volt, etc., all the way to essentially 1 step less than the 16 volt because of the voltage divider 50K additional one there. So essentially for this configuration, we will have 2 times, if we have n bit, we will have like 2 times n plus 1 amount of resistors used in this, 2 here on each bit, and then 1 additional one on the op amp. Any questions so far on this one? So, we're basically dividing it every time by 2, and then using that amount as the lowest step of our DAC converter. And then basically, individually turn on and off each of these switches and then add it up to a value on the V output. Hope that makes sense. More or less? Okay, cool. And just to make things a little bit more complicated, there is also similar to this idea, but they have this binary weighted resistor DACs. And instead of using the same value, R and 2R, it basically uses R or R divided by 2, R divided by 4, and each bit of this digital output is contributes to like a proportional voltage. And for this one, it's similar to the previous one, but this one will be a little bit harder to manufacture because we have like more voltage values to deal with, and each of these have to be like more precise in order to have a high precision or high accurate DAC. But usually it's much easier to manufacture something in the same value in a larger quantity and also like a higher accuracy rather than manufacturing a bunch of things at different values with the same accuracy. But this is essentially a different configuration, but based on the same idea as before. And of course, we're gonna have another demonstration here. So this one is it's pretty straightforward. Basically, if you it starts with 0, and then you have 1 bit, you get to 1 volt, and then you turn one on is 2 volt, and if you go all the way, it's essentially 15 volt. It's again a 4-bit DAC, and then each step is 1 volt as before. The advantage of this one is it's from like a hardware perspective or like from like a circuit building perspective, this one is simpler because it uses even less resistors. Previously we use 2 times n. If consider n bit, we use 2 times n plus 1. This is basically just n plus 1. So all of these different configurations using the same voltage divider idea is an effort to reduce the amount of hardware being used. But there is no like strict good or bad between them, just depends on what's the trade-off you're having. And if you have any cost constraints versus if you are more space constrained. But the underneath ideas are held the same within these. Basically use different values of resistors, divided the reference value to different steps, and then selectively turn on which step is being connected to your V out, and then that's your output value at that cycle, essentially. Does it make sense so far? Okay. Cool. So yeah, just as we said it before, and I think someone actually mentioned of these little steps. So all the DACs have quantization arrows. This is pretty much defined by the least significant bit of your DAC or ADC, the smallest steps you could have. And there are some ways to just smooth it out by adding an additional like low pass filter, etc., or like adding an additional RC circuit to make it smoother. But these things are inherently inside of all the ADC and DACs. So for the next part, let's take out an exercise on the class worksheet, and then let's try to fill it out on this form. You can rank any of them as high, medium, low, as well as like speed, resolution, linearity. Linearity is basically how likely each of your steps is the same at different bits of configurations. So like say if you increase from 0001 to 0010, is that step the same as increasing from say 0110 to 0111? And the power and number of resistors and switches. Yep. Feel free to talk to your neighbors, and we will check back in like probably 5 to 10 minutes.
It's like oh my god, this one is it is the linearity of these steps. So with a bending here online, like it's speed. Not only do you have to charge the capacity of the weight for the I think it was large because you have you have high dynamics, which is a lot. So you also have is it one resistor here? You add use linear values. That's kind of what I thought. Yeah, each one has the same stat. Don't
Isn't it the same as all the medium compared to the other two.
Doesn't make sense.
We talked about this one. Yeah, so it has to propagate through that. Well, this is common. You always have your values here. That anytime you switch here, it has to go through.
The binary way that you got the interaction. Wait, no, it's only gonna be like you can click on yeah, I get what you're saying. Like you only have to you tap like you know, but so what?
Like I thought this was like communicating or something.
Yeah, it does. I have no idea.
With the one
I guess yeah.
So, is this drawing the same as this drawing?
Yeah, right.
Yes.
Voltage divider means two.
Important to switches. I still think this is immediately compared
So that's a two actually.
yeah, with this. Yep. This is 2 cars. Oh, wait, this is what we're doing. This is my no, because these silos don't look like so I compared to those two, it's slow. I also think that everything's going on once. I was wondering
I always bet money that I'm not right. So I would I don't think so.
Is this not higher linear than the other?
Yeah.
Actually, I like that one. That looks slow. That looks slow.
Oh no,
Really? Weighted by
no, we showed fields. When he had it all turned on. What? No.
Yeah.
They're all off. I don't know how you're like speed.
This is like all mega. This is so I'd still say. That's the best thing about the hairstyle. Yeah, I yeah. What are the rest of those? Wait, no, just I agree. Low to high. Low to I think we go. That's my
All right, how are we doing? Everyone have some answer written down?
2 more minutes.
Okay, 2 more minutes.
That was my reason. All right, you had your 2 minutes. Let's look at the answer together. Hello, hello. All right, let's look at the answer together. How are we doing on the resolution? Given the same amount of space or area you have on chip or on whatever design platform. Any thoughts? Any answers you want to share? Anyone? Yeah.
For the PWM is the highest.
And then which one would be the second highest?
Either the R2 or the binary weighted.
And the reason for that is?
Because you only need the block with the PWM.
Mm-hmm.
And then the other two sort of scale linearly with the resolution. Just the value scales.
Exponentially.
Yeah.
Yeah, that is, very much correct. We put like the first one to be medium because it's kind of like a trade-off between how much time you put it inside, as well as it's also a little bit noisy because of but essentially you could achieve a quite high resolution with the PWM if you spend, more, but because of it's noisy, we just put like a medium here. But you're absolutely right about the others as well. So the voltage divider will be low because it's exponentially, and the other two are high and medium, or like high and semi-high because it's one of them. They're both linear increasing, so they should be quite comparable. But just one take about twice of the size of the other. So in terms of number of resistors. Any questions on the first one? Hope that. How about the speed? The speed is like the conversion speed of a given digital value to a output voltage value. Anyone want to share their answers on the speed? Anyone? Yes.
The PWM is slow
Mm-hmm.
because you have to charge and discharge the capacitor, and then the voltage divider is probably medium because it just has to propagate through a longer path,
Mm-hmm.
and then the R2 and the binary weighted should be about the same.
I see. Yes. Yeah. Pretty much the same. So exactly. So as you said, the PWM is slower because it take a lot of clock cycles to do one voltage output. Because we have waiting to the charging, decharging, and for the last three, they're actually pretty much the same speed because all of these resistors, they're like hardwired to each other, and then what's taking time is essentially how long it takes for all of these switches to be at this position, and all those switches are essentially in parallel, so they don't interfere with each other. So all three of those are essentially as fast to each other and very fast within like a clock cycle. Usually they're able to just close or pull up the switches and then check out the output value. So essentially one clock cycle or less. Any questions on this? Okay, how about linearity? In case, I probably didn't explain it very clearly before. Basically, this is, imagine we have like 4-bit DAC, then we have like 16 steps. Basically, how close each of these step value on digital to like the actual analog output. So on digital, if you increase from 0 to 1 versus from 14 to 15, the amount of value changed should be exactly the same on the analog output, right? But in reality, each of these two steps, the changes might be slightly different, depends on your DACs configuration or hardware. So this is essentially asking you how close are these each steps have within each of the digital values. Hope that clear out some confusions. And whoever wants to share their answer on this one. Okay, people are nervous. Okay, we can look at it together. So basically, what do you guys think about like the PWM, the linearity? It's probably going to be pretty low because it's quite hard to have like a very like a precise control over like a RC charging time, especially the charging time itself is not really linearly. And for the voltage divider, and the latter three, is usually depends on the hardware, how easy it is to find the high accuracy hardware within the industry. So the voltage divider is going to be the highest because it's using the same value of the resistors over, and it's much easier to produce the same value of resistors with lower error tolerance. And similarly, the R2R ladder, it's medium. It's actually close to the high because they only use 2 values. And then for the binary weighted, it's going to be slightly worse because it uses a bunch of values that's in the power of 2 to each other. So essentially more values of resistors, although it uses less resistors. How about the power consumption? We can just, so basically, the PWM will be like on the lower end because it doesn't require any of these components. And then for the latter ones, because of a bunch of the resistors connected in the circuit, that essentially give you slightly higher power consumption. But they don't have, it's not too bad in general. Yes, questions?
I forget which one, but wouldn't the like R and 2R ladder have more resistors and thus like have a kind of like a order of power consumption bigger than the other?
Yes, so here the power consumption is actually more proportional to the values of resistance put together rather than the number of resistance putting together. So if you say have 2 1K resistors putting serial, then it's pretty much like you have like a 2K resistor putting at once. So although the number of resistance between the latter 3, because of the value they put in the end, it's pretty equilibrium to each other. It's just the number of resistors they had in the circuit. And the number of resistors and switches. I'll leave this one to you. You should know the answer. Anyone wants to share their answer? So PWM is going to be low, so we get that out of the way. What's the number, given like an n-bit DAC design, what's the number of the resistors we needed and switches we needed for the voltage divider? Can you just shout out the answer? 2 to the n, power of n? Exactly. And how about the R2R and the binary weighted? Anyone? Yeah. Which one, for the R2R or the binary weighted?
Oh, wait, 2N plus 1 resistors for R2R.
And how many switches for that?
N switches.
Okay, and how about the binary weighted?
Also N switches, but N plus 1 resistors.
Okay, perfect. So yeah, so this is essentially, yeah, this is the answer. Yeah, take a look at it, might be useful. Any other questions regarding the pro and cons between them? Okay, perfect. So, on the board, we have 2 of these DAC output channels, and we have, 8-bit or 12-bit mode. You can choose whichever one to use. We have its automatic buffer offset calibration. What this means is it will calibrate the whole shifting. It basically shifts the whole steps for you, so you don't have to calibrate it on your own. Essentially, if you have a digital 0 there, sometimes the output V output will be like a small millivolt value there. The system will basically shift that down to 0 for you, so you don't have to worry too much about that. And you also have the sample and hold mode, basically that maintains the DAC output voltage for like a certain period of time, so that on the other end you can start to already calculate some other things. You don't have to keep holding the circuit or your digital value on the input pin. But on the output side, the DAC output side, it held the voltage value for you for a little bit. And next, we will go through the types of arrows in ADCs and DACs. These are shared between them, yeah, in case you are more curious, there are some further readings. But to start with, we have the quantization arrow. And we talk about this in ADCs. Basically, you can think of them, it's like the least significant bit is noisy or like uncertain because, within that one step, it could really be anywhere within that one step. So any values you have, that's like an inherent, like an arrow range of your either ADC or DAC. So, yeah, I hope this is, we talked about this in the ADCs, and there are different ways to deal with it. You can either just shift everything to the middle, or you can, ship it down or ship it up. Just depends on how you configure it. I think that was the most common ways to do, but you can decide how you would interact with it. So quantization arrows, it's something that, it's just going to be there. So we could get rid of it by increased number of bits to your ADC or DAC channel, but essentially the least significant bit, that little arrow is always going to be there. We also have the offset arrow. Offset arrow is like the deviation of the actual output voltage from the expected output voltage. One, like the digital value is 0. You can think of them as, it's something like we just talked about, but you can think of them as we have like a curve, right? The whole curve got shifted up or down in this case. So essentially, this is the offset arrow we had, which is usually be calibrated by, the system will just output digital 0 and then see what's the output on the actual pings and then offset that value to all the future outputs. This is usually handled by the channels internally, and it's pretty easy to calibrate. And, basically STM already did this for you. So you can have like a 0 on the analog output 0. Even the actual, the actual value might not be that. But this is the offset value, one of the easy to calibrate and fix offsets. And to that, we also have the gain arrow. It's the you can think of them as like a slope change, almost like. So essentially, it's when the actual output or input, depends on if you're talking about ADCs or DACs, diverges from the expected value proportionally across all the input and output values. So essentially, the slope is going up and down a little bit. If you think, each of these value points as the points you connect together for the slope, you kind of chose the middle point or the edge point. Doesn't really matter as long as you keep them consistent. So how do we calibrate this? This is also one of the easier arrow to calibrate. Basically, we'll sample a bunch of like known values and then look at the output DAC values. And then we use that to calculate like a transfer function and calibrate the output. Because in this case, we basically assuming them to be linear. So like, a few known values, we were able to just change do like a transition functions between them. Is this, anyone have any questions regarding the offset and the gain arrows? So, okay, the slope and then wherever your curve is, crossed with the x-axis. The offset arrow could be positive or negative, depends on how you configure it, what's the circuit is connected to, or however the DAC was connected, or however the DAC is configured. And we also have the differential nonlinearity. So linearity, we talked before, basically how consistent is each of these steps. So this one is, it measures the duration of the step sizes between consecutive digital codes from the ideal step sizes. So ideally, each step should be just trigger the same amount of changes, but in reality, each of the steps could be a little bit off to the previous one or to each other. So this is what the differential nonlinearity is referring to. It's usually specified inside of the data sheet. They will tell you what's this linearity arrow is. They basically call it like NDNL, and then it's usually less than or equal to like 1 least significant bit value of your DAC, if it's a good one. But basically, whatever the value they give you in the data sheet, it's the worst value of this component. You can expect it to be better than that, or like not worse than whatever the X gives you. And the X they give you usually is in the unit of what's the least significant bit steps. So if it says like 0.5 of your least significant bit, then that means if you have a 2 volt and with a 10 bit, that roughly corresponding to like what 2 millivolt. divided by 2, there's a 1 millivolt arrow. They are, of course, because it's compared to the previous steps, they are different types of these. You don't have to know a lot about this, but basically, depends on however your hardware configuration or hardware components you used, they could cost various ways of shiftings between each of the steps. This is usually caused by hardwares. For example, the voltage dividers you used, or like divider types of DAC configurations you use, the resistance you chose is not accurate enough. So depends on how you connected them. The accumulated arrow or the arrow can be a little bit random. Yeah, this is a little bit hard to get rid of. Usually you just test all the values or you switch to better hardwares. And we also have integral nonlinearity. It's essentially, you can think of them as like integral of the DNL arrows together. It's usually represented by the maximum derivation of the actual DAC output from like an ideal straight line configuration towards the actual output. So usually, so for example, this line here will be the expected or like the ideal linear line, and then the actual line is something like that, and this is like the largest arrow between the actual output and the expected output on linear configuration. This is also a little bit harder to get rid of, but usually you either just, if you want to have something really accurate, you can just test all those steps or switch to like better hardware, essentially. Okay, so to give you like some quick overviews on different type of like arrows. The absolute arrows, we talk about like the offset for like the integrated nonlinearity, the differential nonlinearity, and these arrows, every of these arrows is specified. It's going to be specified in your data sheet, and in the data sheet, that number is going to be the worst case scenario. So you can always expect it to be no worse than that. And yeah, I think what the important thing, or like more commonly used in our class later, is going to be the quantization arrows, the full scale arrow, and the offset arrows that we mentioned before. The other, integral linearity and the differential integrality, we're going to be just know they exist. We're not going to test you on that or anything. So quick repack of the class. Basically, we talk about the different types of ADCs, and then we talk a little bit about what type of DAC channels you have on your board, as well as different types of arrows that could be occurred on the DAC and ADC configurations. Those arrow types are shared between ADC and DACs. Cool. So if you have any questions, feel free to come down to me. If you are the project team number 2, if any of you guys are here, please come down to me. And the rest of class, feel free to go. Or if you have any additional questions regarding class, exams, etc. Don't forget to leave your worksheet.
Is the revision due tonight on the project proposal or on Wednesday? Saturday? And then do we just share like
Make sure you have
okay, awesome.